Today we're doing a full forensic analysis of something called MongoBleed. It's a really critical vulnerability that popped up at just the worst possible time, letting attackers literally pull sensitive data right out of a server's memory. So let's get started with the autopsy.
So, I want you to imagine this. You wake up, it's Christmas morning, you're not thinking about work, you're not thinking about code, but then you see it. A proof of concept for a major database vulnerability has just been dropped for the whole world to see. Well, for sysadmins everywhere, this wasn't some hypothetical. This was day zero for a brand new thing.
All right, so here's how we're going to break this down. First, we'll look at the breach itself. Then we'll jump back in time to a ghost from 2014. After that, we'll see how the protocol is supposed to work. And then, of course, how attackers completely break it. We'll look at the real-world chaos this caused for a company like Ubisoft, and we'll wrap up with a really big question about software safety.
So what is MongoBleed, really? Well, at its heart, it's a flaw that lets anyone on the internet, and I mean anyone, no password, no credentials needed, connect to a MongoDB server and basically trick it into sending back raw chunks of its own memory.
And look, this isn't just some simple bug, this is a catastrophic failure in logic. The server leaks what we call uninitialized memory, which is just a fancy way of saying it's leaking leftovers. And those leftovers can be anything the server just finished working on. User data, private keys, you name it.
Now, what's so fascinating about this is that we have seen this exact kind of bug before. I mean, to really get what MongoBleed is, you have to go back about a decade and look at a vulnerability that just shook the entire internet to its core.
It's almost a perfect mirror image of the Heartbleed vulnerability from 2014. You see, Heartbleed went after OpenSSL, which handles encryption. MongoBleed goes after MongoDB. But the method, the actual mechanism, it is identical. It's called an out-of-bounds read. You just convince the server to read a little too much memory and send it back to you. It's the same ghost, just haunting a different machine.
Okay, so before we dive into the exploit, let's take a quick look at how things are supposed to work with MongoDB. You know, the happy path, where everything is running just as the designers intended.
It's pretty simple. A client sends a message. It's in a format called BSON. And to save bandwidth, that message can be compressed. Now here is the absolute most important part of this whole thing. This all happens before you ever have to log in. That means the vulnerable code is sitting right there, exposed to any attacker on the internet.
So how does an attacker weaponize this totally normal process? Well, it all comes down to one tiny piece of information they get to control during that initial handshake. It's really just a simple deceptive lie.
You know, the classic XKCD comic about Heartbleed explains this perfectly. It's like the client makes a really simple request. It says, "Hey server, can you reply with the word hat?"
But here comes the lie. The attacker also says, and by the way, the word hat is 500 letters long. The server, because it trusts the client, goes, okay. It sets aside enough space for 500 letters. It writes in HAT, and then it sends back the entire 500-letter buffer, including the 497 bytes of whatever random junk was sitting in memory right after it.
And that leftover junk, that's the jackpot for an attacker. That's the uninitialized memory we were talking about. It's not empty space. It's filled with the ghosts of whatever the server was just doing. Maybe it's metadata from another user's search, maybe it's internal system keys. It's all just sitting there, ready to be scooped up.
And this isn't just a funny analogy. This is exactly how the real exploit works. If you look at the public proof of concept script, it literally comes down to one variable, buffer size. The attacker just sets this to a massive number, sends a tiny bit of data, and the server blindly obeys, allocates way too much memory, and sends it all back.
You know, the attack can get even more precise. The system's memory manager, glibc, it organizes memory into different sized chunks called bins. So by carefully picking their fake buffer size, an attacker can actually target specific bins. It's like they're hunting for data of a certain size, trying to increase their odds of finding something really juicy.
So this isn't some abstract theoretical problem, right? This memory leak turned into an absolute real-world disaster for the gaming giant Ubisoft.
So, according to the security intelligence group VX Underground, here's what happened. The attackers used MongoBleed on one of Ubisoft's public databases. From that foothold, they were able to pivot, get into an internal code repository, and steal a ton of source code. And that, well, that led to complete chaos. Just how much chaos are we talking about? The hackers used their access to gift over $339 trillion worth of in-game currency to players in Rainbow Six Siege. I mean, think about that. One little memory leak snowballed into a complete meltdown of their entire game economy.
An incident like this, it forces us to ask a much bigger, more fundamental question as software engineers. See, MongoBleed was possible because MongoDB is written in C++, a language where you have to manage memory by hand. So, could this all have been prevented?
The question that was on every developer's mind was this. If MongoDB had been written in a memory-safe language, like Rust, would this have happened? And the answer is, well, it's complicated.
So technically, yes, Rust would have prevented the data leak. In Rust, when you try to do something like read memory you're not supposed to, it doesn't leak data. Instead, it panics. It just crashes the entire server process to stop anything bad from happening. So you end up with a choice. Do you prioritize keeping your service running, or do you prioritize protecting the data no matter what?
And that right there is the fundamental trade-off. C++ chose availability, and in this case, it leaked data. Rust would have chosen data integrity, and it would have taken the service offline. There's no easy answer. It's a tough choice that engineers have to make every single day. What do you protect first, the data or the service